Dear colleagues, I would like to present our joint work in the frames of Christian Doppler Laboratory, here a chair of simulation and modeling of metallurgical processes, Technical University of Leoben in Austria, on the topic of multiphase and magnetohydrodynamic phenomena in the continuous casting process. In my presentation, I will start with a brief introduction and go into the details of each specific topic, coming to my conclusions and outlooks. Our chair is led by key researchers Professor Karisha and Professor Wu, as well as Associated Professor Karimi Sebaki. And as you can see, our group is involved in numerous topics in metallurgy, solidification, multiphase flow, and we are not only focused on industrial applications, but also perform fundamental investigations. The research field of our department can be split into these three main branches. Each of them has numerous subtopics, and they are solidification melting, slag interactions, and plasma applications. And in each of these fields, we have experience on the level of a couple of decades. Today, I would like to focus on the multiphase phenomena during continuous casting process. And it includes such subtopics like highly turbulent melt flow, superheat distribution, and the interaction with the continuously growing solidifying shell. Of course, the behavior of the meniscus area of the slag band is of the high interest, with possible slag entrainment mechanisms and the ways to compensate and fight with this undesired phenomena. And of course, the motion of the non-metallic inclusions coming from the continuous casting tonnage cannot be excluded from this topic. First of all, we'll consider solidification phenomena during continuous casting process. The continuous casting process deals with different types of the final products, such as conventional slabs, billet casting, some special types like beam blank, or highly trended thin slab or strip casting with high throughputs and high solidification rates. And disregard of the final product type, we have to deal with the continuous growing solidified shell against the wall of the water-cooled copper mold. The heat extraction in the copper mold is a result of a complex conjugated heat transfer phenomena. It includes heat conduction in the water-cooled copper plates, heat transfer in the solid and liquid slag skin, as well as accounting for the formation of the air gap due to the solidified strand shrinkage, and heat conduction through the solidified shell into the liquid melt pool, which causes the formation of the new solid, which is in its turn continuously withdrawn from the continuous casting mold. To account for such phenomena in the numerical simulation, we need an extensive industrial data, such as temperature measurements at the real casting line, or experimental data, for example, for secondary cooling zones, where the performance of the water nozzles are estimated based on the inverse heat conduction problem. Conventionally, the motion of the solidified shell is described by static distribution of the casting velocities. However, such approach is insufficient if we would like to predict more complex phenomena such as crack formation, depressions, and other mechanical defects. Thereby, a rheological model for the solidified strand must be applied, such as viscoplastic model, where the mechanical properties of the solidified shell are described by nonlinear functions of the local strain rate. Thus, based on the dynamic calculations, we can estimate local stress distribution and apply critical thresholds for formation of different defects. Going fast forward, we can even apply our multiphase and heat transfer models to simulate the initial solidification at the meniscus region. The solidification during continuous casting process is supplemented by numerous multiphase phenomena, and we'll immediately go into the more details. The Lagrangian particle tracking is one of the key topics in multiphase modeling for the continuous casting process. Actually, it can be applied both for non-metallic inclusions motion and for the distribution of the gas bubbles. In our studies, we have performed one-to-one scaled continuous casting Tandish water modeling by injecting the particles of different sizes, starting from big diameters and ending up with very small fractions, which were, as you can see, almost like dust clouds in the experiment. Based on the experimental results, we have verified the accuracy of our models for different particle sizes, as well as estimated the importance of different forces which act in the turbulent flow on the particle motion and their distribution. Consequently, after verifying our particle tracking models, we have applied them for industrial cases such as non-metallic inclusions motion on top of the highly resolved turbulent flow in the continuous casting Tandish, and estimating their ratio being captured on the top surface of the Tandish or escaped through the stopper rod gap into the continuous casting mold, where we have tracked their further fate as passive tracers on top of the turbulent flow, or even performing the two-way coupling, where, for example, injected argon bubbles could also modify the background melt flow. The meniscus behavior is one of the crucial points for the continuous casting process. We have studied both experimentally and numerically different regimes, trying to track the criteria for the slack entrainment. So as you can see, with growing throughput of the fresh melt, the distortion of the slack bend surface appear, and finally, due to the shear stresses, or as in this example, due to the formation of the local vortex, a part of the slack droplet can be dragged away, but the most dramatic scenario happens when it meets a fresh melt jet. It emulsifies, and then it's almost impossible to extract it back to the slack layer from the molten steel. Additionally, we also investigate the fluctuation of the slack bend layer, since continuous oscillation of this slack position can cause the erosion of the refractory materials. We are continuously verifying our multiphase flow simulation, both in regard to the turbulence modeling and to the free surface behavior. As you can see, we study conventional scenario shown on the left animations when the traditional double roll pattern is observed. However, we also tune our models to resolve such non-trivial cases as formation of the single oscillating jet in the four-port nozzle. Thereby, we verify mesh resolution and modeling technique in respect of the subgrid models, which can correctly resolve flow separations and flow oscillations. Logically, we come to flow control of the multiphase phenomena in the continuous casting process. And the electromagnetic braking is one of the well-known techniques for that. The electromagnetic braking represents transversal distribution of the applied magnetic field. It can be uniform or localized. Here we present two comparative cases without applied magnetic field and with EMBR. As you can see, the applied magnetic field strongly changes the flow pattern, dampening the flow fluctuations, controlling the meniscus flow, and redistributing the superheat. In the case with applied electromagnetic braking, the superheat remains at the top part of the continuous casting mold, providing better melting of the mold flux and resulting in more uniform slack skin formation and stable solidification of the melt inside the continuous casting mold. In our studies, we have systemized the effects from the applied electromagnetic braking in relation to different flow issues which can occur in the continuous casting mold. They can result, for example, from misaligned submerged entry nozzle, or due to its partial blockage during clogging, or because of formation of natural melt fluctuations in form of vortex street or single oscillating jet in transversal direction between the narrow walls. It was revealed that most of the issues can be already resolved by applying symmetric magnetic field. However, some of them require adjustable technique when the magnetic field is varied between left, right, or top and bottom sides of the mold. However, some of the issues are even worsened by application of the magnetic field, when the asymmetric flow pattern is frozen and it causes the strong remelting of the solidified shell. In such cases, some other countermeasures must be applied. We can clearly apply our designed multi-phase models in the development chain, starting from recording industrial issue, simulating and suggesting possible solutions, and performing this iterative process until the goal of the industrial partners is fulfilled. What is drastically important in our investigations is that we apply the fundamental studies into the industrial practice. For example, we have researched on restructuring of the submerged nozzle jets or upper and bottom rolls under the applied magnetic field. These results were assembled based on the intensity of the applied electromagnetic braking to predict when the secondary or ternary MHD structures can be formed. We also granted an intensive attention to the interaction of the induced electric currents with the solidified shell. As you can see from these very representative animations, the role of the semiconductive solidified shell cannot be neglected, and it strongly alternates the turbulent flow inside the continuous casting mold. The distribution of the induced electric current must be also carefully treated at the interface of the liquid melt and second non-conductive phase, for example, slack bands, gas bubbles, or entrapped slack droplets. Certainly, all high-fidelity models which I have presented today cannot be directly applied for the online control of the industrial process. However, they become an ideal source for building up different regression models, which in turn can be used later in machine learning. In this example, the transient history of oscillating meniscus is decomposed by using only 5 dominant modes. When the time coefficient matrix is applied, the meniscus history can be reconstructed for any time instance with very high accuracy level. Our multi-phase models were not only employed for the industrial applications, but we also had a great honor to present them for the continuous casting community in the form of the publications. This list contains the selected studies, and we highly welcome you to follow for the further details. With that, I really appreciate your attention, and thank you for staying with me during this presentation.